So you just saw one example of how to solve a trig equation. And like with verifying identities, when you are solving trig equations, there are going to be different approaches that you can use in order to accomplish your task. Excuse me. You're still going to be using algebra and trigonometric identities to help you accomplish the task, but how you use those things can be a little bit different depending on the kind of equation that you have. So we're actually going to take 2 days with this, and I'm going to go through several different kinds of equations with you. We're going to see 3 more examples today, and then next class you can watch another video that'll take you through 2 more types of examples, and then you can work on the practice for this lesson. Now what you need to understand here is that unlike identities, these are not statements that hold true for every value of the variable. These are back to being equations where there are certain values for x or certain values for your variable that are going to make your equation true, but it is not going to be true for every value of the variable. So these are not identities, these are back to solving equations, and we're trying to find what are those specific values for x that will actually make our equation true. So in the first example, I would call that an isolating a single trig function method. You had a fairly simple equation that had a single trigonometric function in it. Your goal was to isolate that trigonometric function so that you could then find the values for the x, or the angle measure, that would give you the answer that you were looking for. Now, I will tell you that although it does not have to be the case all the time, we are going to work with equations where the answers you are going to get are going to be answers from the unit circle. So you're going to revisit those values that we talked about last chapter and those sine and cosine and tangent functions from the unit circle that we talked about last chapter. All right, so let's take a look at example number 2 now. In this case, we have an equation where we have 2 trig functions. But they are the same trig function. They're both sine functions. And so in a case like this, where we have more than one trig function, but they are the same trig function, we want to collect those terms together. And any terms that are not like that, we want them to be on the other side. So I'm going to add this sine x over to this side with this sine x, so that here things will cancel and I'll have a 0. And then here I'm going to get 2 sine of x plus our square root of 2. Now the square root of 2 is not a like term, so we're going to move that over to the other side by subtracting that. And then to get our sine of x completely isolated, we'll divide both sides by 2. So we end up with the sine of x being equal to negative square root of 2 over 2. And so now we want to figure out x. Since x is inside of the sine function, x represents an angle measure. So if we think about our unit circle again, we're trying to figure out what is the angle rotation around our unit circle that could give us a negative square root of 2 over 2 answer. Now keep in mind, if you were to put this into your calculator, which I don't recommend you do because you're not going to get exact answers, but if you did, you would be doing an inverse sine of both sides, and your calculator would only give you one value. That does not necessarily mean that there's only one value that works. It just means that as a what do I want to say? As a function, there's only one possibility that works. Okay? But we have to think beyond that because we're not limited to just a function here. This is just an equation, and in our equation, we can have lots of different values for x. So you'll notice I don't have any restriction here about being from 0 to 2 pi. You saw that in example 1, so you were only looking for the answers from 0 to 2 pi. But here I did not give you that restriction. So what do I do with this? How do I get my final answer? Well, let's start with a reference angle. If this was a positive square root of 2 over 2, and we did not worry about that negative for just a minute, where would the angle be? Well, if you got used to the 5-finger rule, using that little trick for sine and cosine, you can go back to that. We're just going to use it in reverse. We know we want sine to end up being square root of 2 over 2. So we have to figure out which finger do I put down so that I end up with sine, which has to be on the right side, being a 2 because it's square root of 2 over 2. So that means it's this finger that needs to go down. And if you remember, this finger represents pi over 4. So as a reference angle, we're talking about pi over 4. And I highly recommend you do this in terms of radians. Because once you know the denominator of this reference angle, you can figure out any of the other possible angles in any of the other possible quadrants. Okay? So we got a reference angle of pi over 4. But then the second consideration is which quadrants would we be in? If this really is supposed to be negative square root of 2 over 2, in which quadrants is sine negative? Well, that's going to be in quadrant 3 and in quadrant 4. So I need angles that have a reference angle of pi over 4 but are in quadrant 3 and quadrant 4. Okay, so which angles are those? Well, the quadrant 3 angle is going to be here, and that's 1, 2, 3, 4, 5 pi over 4. And then the quadrant 4 angle is going to be over here, so if I keep counting, there's 5, 6, over here is going to be 7 pi over 4. And if I had the restriction of only looking for answers from 0 to 2 pi, I would be done. These are the two values, the two angle measures from 0 to 2 pi that would make this equation true. But as I mentioned a moment ago, that was not the case. So what that means is that we're not limited to just one rotation around the circle. We can keep going around and around and around and around, and every time I get to this spot, it's an answer, and every time I get to this spot, it's an answer. So how do I indicate that? Do I have to list out every possibility? No, because you can't. There are infinitely many possibilities. So instead, we indicate that we could keep going around the circle and around the circle and around the circle as many times as we want. We could even go the negative direction around the circle. That would work too. And every time I get to that spot, there's an answer. And every time I get to that spot, there's an answer. So we do that by saying we're going to add 2 pi n to both of these answers. Why 2 pi n? Because 2 pi is the period for sine. So that means when I get here the first time, to get back to this same answer, this same position, I have to go all the way around the circle, 2 pi radians, to get back there again. The n represents an integer. And it represents how many times we go around the circle. So if I get a positive 2, then it means there's my answer, there's 1 more time around, there's 2 more times around, and whatever angle that would actually be, whatever rotation that would actually be, that would be another possible solution. If it's negative, let's say a -1, then I would come negative to get to that answer, and then going around in a negative direction 1 more time would get me to an answer again. So this is how we indicate if we're talking about all possible solutions. 2 pi because of the period of sine, and n to represent how many rotations around we're talking about. Okay, and so this is the final solution we're looking for. Okay? All right, let's try another one. In this example, we are going to have to take square roots. We have a single trig function again, similar to what we saw in the first example, but in this case that trig function is squared. So we're going to need to go through the steps to get the trig function isolated, and then when we do, we're going to have to take a square root to get it completely by itself. So my first step is going to be to add, the 1 to both sides. And then I'm going to divide both sides by 3. And I end up with the tangent squared of x equal to 1/3. Now, when I take the square root of both sides, we have to remember that because this is one of the steps in solving an equation, it's going to be plus or minus the square root of 1/3. Now when we talk about tangents on the unit circle, we didn't really have an answer in this form. But that's because this form is not completely simplified yet, because technically that 3 in the denominator is still under a radical sign. So we want to simplify this. Square root of 1 over square root of 3. Square root of 1 is just 1, so we really don't need the square root sign. And then multiply top and bottom by square root of 3. So we end up with plus or minus square root of 3 over 3. Okay? All right, so now which values of x give us a tangent that is square root of 3 over 3? Okay? Well, again, we need to talk about reference angle, and we need to talk about quadrants. Okay? Which reference angle is this going to be? Well, if I want square root of 3 over 3, remember that came from 1 over square root of 3? And it's sine over cosine for tangent. So again, going back to our finger trick, we need to know which finger to put down so that my sine is going to be 1 and my cosine is going to be the square root of 3. And that ends up being this finger. The sine is 1, square root of 1, and the cosine is the square root of 3. So this finger represents a reference angle of pi over 6. Okay? Then, which quadrants are we in? Well, since our answer can be positive or negative, we're in all of the quadrants. Okay, so what are the angle measures in all of the quadrants that have a reference angle of pi over 6? They would be pi over 6, 2 pi over 6 is really pi over 3, so that one doesn't count. 3 pi over 6 is really pi over 2. 4, then we'd have 5 pi over 6. In this quadrant, we would have 7 pi over 6. And all the way over here, we would end up with 11 pi over 6. And again, because there's no restriction about which values of x we're looking for, we need to add our multiplier. But in this case, since we're dealing with tangent, the period for tangent is only pi. So when we add on the multiplier, it's going to be a pi n rather than a 2 pi n, because the period for tangent is pi. Okay? Now you may realize here that if I take pi over 6 and add 1 pi to it, I get 7 pi over 6. So if you want to take these two out, because these two already include those answers in them, you are totally welcome to do that. But if you just want to make sure you've got everything covered, having all 4 of these is also totally fine. All right, let's take a look at one more for today. Here's example 4. And in example 4, we want to think about factoring, because factoring is an algebraic means that we can use to help us solve equations. Okay, and in this case, let's go ahead and put the restriction that we only want solutions from 0 to 2 pi. Okay, so when you look at both sides of this equation here, where we have cotangent x times cosine squared x equal to 2 cotangent x, what do you think we should do first in order to start solving this equation? Well, a lot of people will look at this and say, oh, I have cotangent x on both sides. Let's just divide that and get rid of it. And although that seems like a good idea, it is not, because that cotangent x includes a variable. So by dividing out this trig function, you are getting rid of one of your variables, which means you are potentially ignoring one of your possible solutions. And so one of the solutions may not show up in your answer because you are getting rid of this cotangent x. So we never, ever want to divide both sides of an equation by something that has a variable in it. If it's just a number, that's fine. But if it has a variable in it, that's not a good choice. So what should we do? Well, we're going to work this just like we would with a quadratic. We're going to get everything on one side of the equation and set it equal to 0. So I'll have cotangent x times cosine squared x minus 2 cotangent x now equal to 0. So now we can look at the fact that these two terms both have the cotangent, and we can factor it out. We are not dividing it and getting rid of it completely. We are simply dividing it out as a factoring technique. And so that leaves us cosine squared x from the first term and minus 2 from the second term. And that's all still equal to 0. Okay? And so now, Because I have factored these, I can use my zero product property and set each factor equal to 0. So my cotangent of x will equal 0, and my cosine squared of x minus 2 can equal 0. Okay? All right, so now, how do I find where cotangent x equals 0? Well, unless you have a really good memory, and you remember this from the unit circle, it might be easier to change it into cosine x over sine x equals 0. And when you think of it in this way, the only way this fraction becomes 0 is if we make the cosine of x equal 0. So what are the values of x that will make cosine of x equal 0? Well, those are the axes, right? So cosine is x, means we need to be on the y-axis. That means an angle of pi over 2 and an angle of 3 pi over 2. Okay? And we don't need to add the multiplier on because we are just staying within this interval of 0 to 2 pi. Okay? Let's look at our other factor. Cosine squared x minus 2 equals 0. I can take cosine squared x and make that equal to 2. I can square root both sides and get plus or minus square root of 2. But then what is my x value going to be? This doesn't look particularly familiar to us as being a unit circle value. And if we really think about this, the square root of 2 is approximately equal to about a 1.4. Now remember, when we're talking about a parent function like cosine x cannot be bigger than 1 or smaller than -1. It cannot go beyond that range of -1 to +1. So this is going to be impossible. There's no way we can get cosine of x to equal a positive or negative 1.4. So what that tells me is that this factor does not give us any other viable solution. So the only values that actually work in this case are the two that we got from the first factor, our pi over 2 and our 3 pi over 2. All right, I think that's a good place to stop for today. Let you think about those a little bit. We'll continue with this tomorrow with our next lesson. I'll show you a couple more examples, and then you'll have a chance to work on your practice after that. Okay? If you have any questions about the 3 or 4 that you saw today, rewind, look at them again, make sure you understand the process that went into these examples for today. And we'll continue with this tomorrow. We'll see you then.